in 1993. He received PhD in 1993. He is currently working as outstanding scientist and deputy director, antenna systems area. He has worked as guest scientist at German Aerospace Center in 2001. He was the designer of shaped reflectors and guided dual graded reflector antennas, high power helix antenna, multiple beam antennas for various INSAT and GSAT programs. His current areas of interest are metaspace based reconfigurable antennas, contoured beam reflector antennas, and digital beam forming based antennas. He has led the team to develop the antenna systems for navigation satellites, radar imaging satellites, and Chandrayaan 2 and 3 missions. Sir is recipient of Space Gold Medal of Astronautical Society of India in 2005, ISRO's Team Excellence Awards in 2007, 2008, 2015, and 2017. Sir has more than 85 publications in national or international journals and conferences, and four international patents to his credit. Sir is going to deliver a talk on antennas for satellites. I welcome sir. I request Dr. Sanjeevan Shastri Madam to please welcome him. I request sir to start with this.
Good morning, everybody. Good morning. Sorry, I think I got delayed from scheduled your time. Sorry, my apology for that. मराठी आहेत की मिक्स म्हणजे मध्ये मध्ये मराठी बोलून चालेल आणि you can interrupt me at any time wherever you find doubts or wherever you may ask any question. Don't be afraid be asking the question. Why I मला बिलकुल शंका करत मी असे प्रश्न का विचारतो कारण की शंकाने आपलं नॉलेज क्लिअर होईल किंवा शंका कन्सेप्ट क्लिअर होतील कदाचित तुमच्या काही प्रश्नांची उत्तर माझ्याजवळ नसतील पण we will find out the solution subsequently also. So don't hesitate in asking in between also. Okay, my today's talk is on the advances in phase array antenna technologies for space application. This is the topic of interest of currently to the base either on the satellites or even in the ground station antennas or even from the various defense establishments. So this kind of type of antennas are really very much key to advanced technology development. There are various ways of doing it that I will try to cover it in this lecture. Is not the phase array technology per se. The concept is very old. We'll see how they are. Now, if I see the applications. Now the phase array antenna for space application. If you see, there are different, I just split into the two domains. One is the for this onboard application. When I see onboard, it means for the with the antennas which are flying on the spacecraft satellites, and the application for the ground application, though it may be communicating with the satellite. So I have just differentiated into the two. One for this phase-borne applications, that is an onboard application for communication, not necessarily communication. It can be navigation or remote sensing satellite also. The ground application from which is communicating with the various spacecraft. Now, one of the antenna the requirement is a steerable beam antenna from LEO and NEO satellites. What happens when? Why do we need this kind of failure, having the steerability, having the reconfigurability? If you see the over the Earth, if over the Earth there are various kind of orbital satellites. One is LEO, which is flying at the height of around 500 to 1200 kilometers. And if you see their coverage is very small, because like just to assume that suppose I have a torch, and I'm just making it's the beam, the light, the field of view of the torch. You assume it is an antenna beam. If you put the torch like this, what will happen? If you put it very near to the ground, you will find a small circle. The moment you go above, up and up, the field of view increases. Similar thing happens here. Similar thing happens here with the satellite in the lower orbit satellite, which is having had the altitude of 500 to 1200 kilometers. Its coverage is small compared to the entire Earth. The moment you go to the medium Earth orbit satellite, which is 5,000 to 20,000, its coverage is more. The moment if you want to cover with these satellites entire globe, you will be needing hundreds of satellites. With this few tens of satellites, if we go with the geostationary Earth orbit, which is at the height of 36,000 kilometers from the Earth's surface, it will cover 3 satellites are enough to cover the entire globe. Not only the right side also, if we put 3 satellites at 120 degrees apart, they will be covered the entire globe. Now their coverage is big. Though the subtended angle is small, the coverage is big. So based on that, the various where do we need this kind of phasor? Now question comes, where do we need this antenna?
So he is changing
तुम्ही नेक्स्ट म्हणा
नहीं मुझे कर्सर ठीक है मैं picture चलता है when we talk about the now steerable antenna when we from geo, what happens when the distance is large, then the path loss is also more. What we need is a very large gain antenna, order of 35-40 dB. Then if you need higher gain, then you have to have then it will have a smaller coverage. Then it will not have this kind of beam, because when the large coverage, it is just I'm showing the field of view. But the moment my topic of interest will be region of interest will be small, I will be using the very high gain antennas. Then if I have to steer the different region over the globe, I need steerability. And for that steerability, I need a steerable beam antennas. Either it can be phase array or it can mechanically steerable array. Similarly, LEO and NEO, since it is for LEO especially, you might have heard the Starlink or the various OneWeb or other satellites constellation. Recently, Government of India given the permission to use the Starlink satellite constellation for this. They need the orbital period is 90 minutes around they completing the globe. So they are very fast. Even one satellite from the ground, the visibility will be the only 10 to 15 minutes. So then within 10 to 15 minutes, the next satellite will come. So you have to have very fast steerability of the satellite as well as the ground station antenna. For that, you need these steerable antennas. Either for the ground antenna also to track the satellite, even for this LEO satellite or MEO satellite. Similarly, for the MEO also the similar. Now similarly, what happens simultaneously steerable multiple beam generation. This is another application where if suppose I have a spot beams, very high gain beams, and I have to cover the larger area, then there also I need a simultaneously generation of multiple beams from the various either LEO or the GEO. There I also need a steerable antenna. There also I need a phase array antenna. Similarly, inter-satellite link communication. What happens? Various LEO to MEO or LEO to GEO communication. What I have shown here in the different orbit. Suppose when this is communicating, LEO is communicating and is going within 10-15 meters of the circle, then it has to transfer its, let's say there is a call already going on, it has to, there should not be call breakage. So immediately what happens, it has to transfer its call, the content to the geo and geo to next LEO which is coming into picture. So there what you need is a inter-satellite communication. The satellite to satellite communication, there also you need a steerable or a phase array antennas. Now again in data relay application, the other application, what happens is the, for example, the right example is our Gaganyaan. Gaganyaan is also moving in the LEO constellation around 400 kilometers. Now the Gaganyaan to be continuously tracked or continuously to be communicated, it has to, there is a, we have put in three satellites or currently two satellites, the which are, we call it as a Indian data relay satellite. That will be, Gaganyaan will be communicating with the data relay and data relay satellite, because the Gaganyaan will not be always visible from the Indian soil. Because it will be just, as I mentioned, they go immediately 90 minutes, it has to complete the chakra pura Gorman, iska pradakshina karne. That will becomes very difficult to, suppose India is somewhere, then it will be very difficult to have a visibility of satellite which is going beyond its horizon. So then, but the communication should not break. Then it is communicating via geo to geo, since it is always visible, it will communicate to the station in the ground. For that also, those kind of application also, we need a steerable or phase array antenna. The scanning being synthetic aperture radar antenna. Here, this is the one of the remote sensing satellite, radar imaging satellite. There, when we are going over the, taking over the images, that is mostly, those are mostly in the LEO. We have to scan the and take the images, and that imaging also in the microwave, especially in the microwave remote sensing, we need a scanning beam antenna. So then these are the various application where we need essentially the phase array antennas or steerable beam antennas. I will, rather than saying exactly phase array, I will say steerable beam. Now, how do you achieve the steerable beam antenna? There are various technologies available that will classify into the different type of antennas. Similarly, here I mentioned, now again the SATCOM on the move. When even if you are communicating with the geo even the satellite is stable with respect to the Earth movement, but if you are moving on the vehicle, let's say either in the train or in the car or in the plane, then your azimuth elevation angle to track to the satellite changes, and that you need a continuously steerable tracking to the satellite. That is one of the best observed application is for that. The SATCOM on the move for that phase array is essentially required. Similarly, for LEO MEO, as I mentioned earlier, it is essentially required because the satellite is moving fast. And the aeromobile also are nowadays, various aircrafts are also providing the internet during the flight, and they essentially need a phase array because they have to track the mostly the geo. Can you go to the next page? Now we'll come to the topic of what is the phase array antennas. The phase array antennas is per se is nothing different. It is not a tough concept. It's a very simple concept. It's a progressive phase at the input of directing elements. I will show in the slide next. If these are the array elements, different array elements are there. If you have like this kind of phase front, then the beam will come there. If you change the phase front in different direction, the beam will come from the different perpendicular to this phase front, you will get the beam direction. The concept is very simple. Only thing is how you realize it. That's make the different technology. There are various challenging technologies are available to realize this. Simple concepts are also there, difficult concepts are also there. So these are the progressive phase, that is the linear phase taper along the phase, the array of the element that will generate your beam scale. You change the linear phase taper, you will get the beam scale. So these are the, again, the Y phase arrays. These are the, if you see earlier, there is a way of, the question becomes Y phase array, because what happens when you can do it by mechanical steering also. When there is a large antenna size up there, what happens? It's the response time reduces. For example, the various radar on the ground, if you move by mechanical movement and track the in orbit any missile or anything, it becomes very difficult to cope up with the speed of the missile or to speed of the target. So essentially, what we need is the electronical steering wheel. That's the very fundamental application started. The basic phase arrays, electronically beam steering phase arrays started from the requirement from the different wars happened in the history of the world. So that the technology concept is old. the doing the earlier phase array, अगर मुझे बना था इतना पूरा phase array, it used to have a completely big giant room. But not only room, it requires to use volume because there was no miniaturization in the active circuit. So those were the days when phase array was the is the beyond reach technology. But nowadays we'll see in the course of the lecture there it is now you can make in your college very easily and with sitting on your palm top. So these are the and another advantage. It's not only diversity reception. You can having the phase array or having the different control over the aperture. You can really what happens during the scenario different nowadays communication. There are various fixed frequency signal, various applications are going on. If particular direction, if you are getting any interference, you can create a null into that direction so that it is not affecting your the communication. And that may becomes and still your communication direction can link and work and interfering signal you can suppress it by creating a null or suppress side lobe in that direction. That's a very advantage of the similar kind of the phasor. It's not only the steering but also create along with the steering you can create the interference suppression from the your on your beam pattern. The that's okay. This is the steer the beam that is the standard application. Determine the direction of arrival. What happens many times? This is the you don't know where to steer the beam, where the target is coming, where the object I have to steer the beam. The advantage of this phase array, you are having so much flexibility. You can scan the region and you can say that my signal is. There are various methods of doing this direction of arrival. You might have studied it. Either you might have taught rather in your various courses. The various algorithms are available, and there you can see to detect from where the target is coming. The target is coming in that direction. You can steer, maximize the SNR, and accordingly focus your antenna main beam toward that direction. This is the another very important need of the application. This cannot be done by the mechanical only. So it has to be have electronically steering beam antenna. So that and say to maximize the signal to interference plus noise ratio. This is again manifestation of the same application. Same. Then this is now what is design when we talk about the phase array. What are the design goals you talk about? What are essentially required to consider by designing it? What is the scan range I'm looking for? How much? 0 to 60, 0 to 90, 0 to 10, 0 to 5. That depends. That first thing, the parameter you should have. What is the scan range? Then what kind of far field patterns you are looking for in terms of gain, beam width, if it is really high gain, what should be that will be your starting goal, starting parameters for your designing this. Then using the minimum number of elements because the more the number of elements increases, the more hardware and the more the cost and the entire thing becomes very complex. So those are the design goals for the starting point of which should be there, and then accordingly the design. Now this physics of basic beam steering of confidence, as I mentioned, if we focus on this part, as I mentioned earlier, it is very simple. Let's say take up the case of the linear phase array. You can have the uniform amplitude. Now only you have to change the phase taper. This is the phase taper I am showing across this element, and this is the pattern I am showing across this elements array. What happens the moment if I change the beam? My beam is let's say from this direction it is steering because the moment it is going, the beam is going in the perpendicular direction. It is a simple concept. You change the phase taper, you will get the beam direction change. This is the on the simple principle the beam steering concept is allowed. Now the another interesting part. I have to shape the beam. As I mentioned, the null interference creation, that was the one application. Sometimes we have to create a cosecant square pattern. For example, in the flying aircraft need a constant flux, then you need a cosecant square pattern. What is required? Then I'm not only keeping the amplitude constant. I'm playing with the both amplitude as well as the plane. See, this is the red line I have shown. This is the envelope. This kind of pattern I wanted in one plane. Now what I do, I have to see the change the excitation coefficient of these elements. Again, whatever I am showing is only for this kind of linear array. Simple case I have explained. I have to change the excitation coefficient amplitude as well as play with the phase such that I can change. Now if you see at this particular position, this pattern has become exactly like this. It is an other plane is just simply a pencil beam. Now if somebody says just to understand what is the synthesize, how you synthesize in a simple term, the antenna's far field is nothing but the Fourier transform of the what is the aperture field distribution on this antenna size. If I have to, if simple, if I want to arrive at this kind of final excitation coefficient in terms of amplitude phase, if I take this kind of aperture this kind of far field pattern and take the inverse Fourier transform, then I should get the excitation coefficient near to this. Though it is exactly it will not be, but it will be a good starting point for the design to take this get the initial excitation coefficient, and then you need a further optimization. Why optimization is, why it is exactly inverse Fourier transform is not resulting in exact pattern is because it's a truncation of your aperture. As you see in the Fourier, it's the infinite bands are there. If you truncate, the performance will change. Similarly, here also you are changing, truncating the size. Your antenna aperture is not infinite; it is having some finite dimension. So according to that, your exact inverse Fourier transform will not yield. You need essentially need optimization in the both amplitude and phase to get this desired pattern. So there are, this is the just few example, one or two example I showed. There are various things. You can create a null in particular direction. For example, if you want to create, let's say, from particular direction, here I want a further separation. You change now, you will play with not only the phase, you will play with the amplitude, and you can create a null in that direction. So there are various, any type of radiation pattern you can generate. In fact, I will just show, simply say, we had our geostationary satellite where we have to generate and literally footprint like in India, our geographical boundaries. There we have using the shape reflector because it was a fixed beam. But again, it is the synthesis is the similar concept. Again, there is the of course optimization is a complex, but you will get the footprint exactly fitting like your India, our geographical boundary. The power is not going beyond India. It is exactly concentrating only in the our mainland region, mainland region and island. Yeah. So now, if you go to the phase array and this, what is the different types of phase array architecture? One, you can have a passive, active, or hybrid. What do you mean by passive? Because as I mentioned, what is required if it's simple concept, if I want to only steer the beam, I need essentially only the phase shifter, nothing else. If I go in the passive array, in the scanning beam, then I can have a passive phase shifters. Passive phase shifters, it can be a ferrite phase shifters, it can be maybe various reflection type phase shifters. There are various ways of achieving this passive phase shifters. And then what you need is you have to combine the power. You will need essentially beam forming network like either various power combiners, I mean depending on the number of elements, and then you will get the once you combine, you got the particular direction beam. Now either for in case of radar, either it transmit or receive this single transmit receive model you will use, and then subsequently the IF domain, receiver or signal processor. This is the constant part. But in the passive array, this will be the only element. The major part will be the phase shifter, which will steer the beam. What is the required essentially? It requires a high power PWKs or this LNA. But what happens in the disadvantage of this is it's a single point failure. If this amplifier goes, then you are despite having the array, it will completely phase array will collapse. And the next disadvantage is since the phase shifter, though it is low loss, but there is a loss prior to the LNA, so that your G by T or the performance will be poor. But this was the technology still viable when there is a very small element, not there are no element, it will be a low cost solution, that these options can be chosen. So trade-off, you have to choose it according to what application you are selecting, what application is given to you. You can say, I cannot say all the time active array is the best. I cannot say all the time hybrid array is the best. Or you have to see what application. Sometimes the cost is the major driving factor, then you will choose accordingly. Sometimes the volume and power is the available is the major one, accordingly option you will choose. So these are the various factors on which you choose what type of architectures you have to select for your design for having the phase array. Yeah, if you go to the active array, now what happened? Like as I told, this was the in earlier slide, it was only single block was there after various phase shifter. But now what I have done is in the active array, each element is connected to the TRM first, and then the phase shifter. What happens? Then I have used, if suppose there are 100 elements, then there will be 100 TRM. But here, now the transmit amplifier, since it is 100, I don't need a 100 watt single, I will need 1 watt amplifier as 100 numbers. Similarly, LNA will be 100 numbers. The advantage what I got it, phase shifter, okay, I anyhow will be the same. Advantage I got, if suppose if there are some of the element fails, it will not, the entire array will not fail. It will be a graceful degradation. 5 to 10% degrade if the elements fail of these active devices, the performance will be insignificant degradation. So you can still tolerate and you can still communicate. So this is the major advantage is the graceful degradation of the whole phase array. Because the here the contribution suppose it to 1 watt or 2 watt, even if out of 100 watt is a 10, 1 watt के अगर 10 भी चले जाते हैं, तो it doesn't matter because you are hardly losing the 10 watt power, but less 90 is available. So the entire the phase array performance, the degradation is graceful. This is very important, especially on the onboard. There we cannot replace it. Once we have flown the satellite, it fails. One amplifier fails, then we cannot go and repair. Ground we can do it, but on board we can do it. So this is the very important parameter. The graceful degradation is the very important trade-off while selecting the architecture, because the temperature for which it is going, it's going from -60 to +70 or something. That kind of temperature is going for the active devices, and despite having all the passing to the stringent qualification criteria, it happens that either there may be error of the workmanship error, or there may be the devices error, and it may fail. So we have to have a tolerance to the performance failure. So this is the graceful degradation is the major advantage here. You are having just connecting TRM, that will be smaller wattages and smaller specification, and then you are phase shifter. Then after that you will combine this loss, which doesn't matter because you are already given, suppose in receive you are already given gain, that doesn't matter. This will not affect your any G by T or anything. So this kind of structure will have better performance in terms of your more tolerant to the failures, more the better performance in terms of G by T or EIP, because the losses are less. Even in the previous case, even if there is a huge power, after that there is a losses. So ERP will get reduced in fact to the subtracting the losses of those components. So these are the active arrays. Then the hybrid array, some of the cases you can use the combination of both. So those are the hybrid arrays. Any questions? So these are the different the advantage, disadvantage of the different things. As I have already mentioned that, of course, the cost active array antenna, the earlier it was very costly. Nowadays, because of the progress of in case of the 5G and 6G and various things, mobile, there the cost, since the production is in the millions, the cost has reduced significantly of the various MMIC, and the cost has reduced even for the active phase array. Now the key parameters for specifying the active array, if you see this, the operating frequency and bandwidth, EIRP, that is effective rate for scan coverage, beam rate, side lobe levels, what is the tracking accuracy, what are the waveform parameters, whether it's pulse, duty cycle and all, noise figure, these are the order. These various parameters, some of the parameters of the not necessarily to the antenna, but these are essentially part of the array, because phase array, because these are the active devices are part of, like the third model intercept, stability and phase noise, harmonic and spurious, reliability, and the prime power requirements, and these are the various parameters you have to really consider into account by designing the actually phase array. Yeah. Now, if I see the probably I will not go into the detail, because this you might have studied antenna in or you might have taught to your student. These are the basic array factors. When you have different elements M by N array and having the isotropic radiators, then what is this is the array factor you give basic it's a summation of all this integral field. Then you get the very narrow beam in the, that is we are calling it as the array factor, multiplied by the single element if it is not isotropic, if it is having some gain. If you multiply the single element gain with respect to the array factor of combining all, then you will get the entire the radiation pattern of the full array. So that is the thing what it is given in this equation. And now the beam steering degree versus the angle. Suppose here just simply graph I plotted. Suppose I have the to scan the 45 degree, let's say from the aperture plane, then the adjacent phase, depending on this distance between the two elements facing the what is the phase required, adjacent phasing equally, that will be roughly 2.5 times, roughly, then it becomes accordingly the 135 or something, so that it becomes, then beam will get scanned to the 45. This is, of course, the mathematics already there. I just plotted into the graph, and then you can use it. Now the various lattices, I will cover this lattice also, various how they are arranged, the elements are arranged. It can be rectangular, it can be a hexagonal, or it can be circular lattice. Now the beam scanning, what I have shown here, it is the different scanning. Here the red more correct, the more intensity, more gain, and accordingly how they split in different regions. Here, since it is with undervacuum spacing, there are no such various other side lobes or grating lobes are stored. Subsequently, we'll find out how the grating lobes will affect if we not select the properly B and the scan angle properly, how this performance gets affected. Okay, in this, I have shown the what are the another input. Many times, what happens? I need a large gain. So if I go with the individual element, as I shown earlier, if I go individual element, if I go for the TR module, my cost will be tremendous, enormous. That is okay when I trade off this. I need a really the large scan angle, then I will go large means 45, 60 or more. Then I will go for the individual element to be with having the entire either active or the TR modules. But if I don't require that much large scan angle, then what I will do, I will group some of the elements. But I need a large gain. Then to reduce the number or reduce the cost, what I will do, I have to have grouping of elements. Let's say I have done the grouping of elements. Let's say this much large array. Let's suppose if I use this, it will need large number of active modules. Because I won't want that. Let's say my scan angle is very less. Let's say less than 10 degree. In case of geo, it is good enough. What I will do, I will make a large subarray. Then for this entire subarray, I will use only one TR mode. For one phase shifter, when it simply comes, let's say only one phase shifter for them. Effectively, how many sites in this particular specific example, 8 those? Only 8 phase shifter or 8 TR mode is good enough. That becomes I cost, but I have still got the good high gain because I use a larger. Instead of having this how much 64 by 4 element, I am using only the 8 TR modules. I am able to clear the beam, but disadvantage is smaller scan angle. And that's good enough. If that makes serving the purpose, I will select by that. But then selecting the proper subarray is one of the important design parameters. At what level, what size I should be able to tolerate, that is important. 4 by 4, 2 by 2, 3 by 4, whatever it is. That is a design parameter. When you design the phase array, you have to consider that. Now, how does it defines that again the D diagram? That depends on that. If subarray is there, then the distance between the elements will not be taken from this to this. It will be taken one subarray center to other subarray. That will become your D. So if this will be take, then the simple concept is for having the grating lobe. If I have D by lambda is less than 1 upon 1 plus sign on theta naught is your scan angle, then you can avoid the grating lobe. Now I will show what is this kind of grating lobe. This is let's say 4 by 4 array full pattern I have shown here normal case. But if I take if there are the scan angle grating lobe are there, like here, I have scanned the beam last subarray. Equal to the main lobe, there is another lobe, which is called a grating lobe. It is taking the max. It is also taking the significant amount of power. So this will be the disadvantage of having the subarray. But if you are able to tolerate it, if suppose then I will not move from this much degree. I will move smaller scan angle because that was the requirement itself. Then I can tolerate with the lobe. This side lobe, this side lobe. This is called a grating lobe. This will be governed by this criteria. Then you can really, then for subarray you will have to follow this. Instead of the single element, you will use subarray distance center to center. Then accordingly you select for given subarray distance center to center, what is the maximum sin theta naught scan angle I can tolerate. That will give us, you can reduce the grating lobe level, and accordingly, because grating lobe will also take a significant amount of power in the undesired direction. So that will be, until by design you have to suppress it. So this is the essentially you will trade off with reducing the number of elements, tolerable getting low, and governed by the your scan angle. Another parameter while we choose the subarray, what happens? The phase quantization. When I see like can you go to the previous slide? Had it been a single element, each this is having the phase shifter, I would have got the phase taper as I showed in the earlier slide. It would have got very good, nicely linear single line fitting y equal to mx. But what happens if I have made the subarray? So for this four element, I got the constant phase. And again, there will be jump for next four array, you will see. Now, can you go to the next? So this is this concept I am showing here. So when I do, what is the when the quantization comes for sub array, less the four element, there will be constant phase. Again, next there will be another phase. So this kind of step performance will come on the aperture phase distribution. Instead of ideally you would have designed wanted the spatial state line. So this kind of the staircase phase distribution will generate a quantized noise, and that will be that will be seen in your the radiation pattern also. So this kind of the content you have to see how much you can tolerate, and again the trade-off parameters are same. Considering that if they are tolerable, you will select that you will still have the knowledge and still proceed for the design. So these are the aspects you have to keep in mind while designing. Yeah, another the design considerations for the phase array are the if you see the what are the what is the factor is the suppose if I take odd number 1:9, that's 9 element. What happens in designing odd number of power dividers? It becomes slightly tricky. That's why choose the symmetric binary fitting network for subarray to minimize the dispersion. So if I can have very good 1 to 2, 1 to 4, and in the order of 2 raised to m, that becomes a very straightforward or easily good performance can be achieved. So accordingly, the elements can be chosen. The modularization in the types, so that let's say full array is there, subarray there, I should select such that I can place properly modularizing, and accordingly I will select their power distribution. So this thing aspect has to be kept in mind while designing the phase array. These are all practical concepts which are very important if you make to start the designing of the phase array and develop. If you are being asked by somebody, then this becomes very important. The another important between the elements is while this choice of the element is very important. The distance I have shown what is how we have the effect element to element spacing. The parameter which affects is the coupling between the array elements. The moment if you scan the beam, what happens? The radiation pattern to relative coupling between the element to element, and then even the surface currents if they are there, that will cause mutual coupling, and that has the types of relative coupling. It can be relatively, it can be surface level, it can be feed network. Surface level means if it is a let's say patch array, and if you are scanning it, then along the dielectric substrate also the feed is going, then you have a surface level coupling. Feed network to network, if they are coupling even the feeding network, then also there will be a performance degradation. What kind of to what extent the performance can go? I am just showing here. That is the phenomenon is called scan blend. If let's say you have to scan large scan angel, what happens? Let's say my the dotted pattern is showing the element pattern. What happens if this element pattern is very smoothly behaving like Gaussian beam, having this kind of extent, no beam. But if this is the troubling parameter, if the coupling is not properly designed or not taken care, what happens? This element pattern will not be like this in the presence of other elements. What happens? Then it will create a null. You assume that my element pattern is very fantastic. It is just equivalent to the cos to the power n theta. It is smoothly uniformly falling, but in actual case, it is not. Many times you will see pattern performance are designed nicely, but I have scanned it. I am not getting power there in particular scan. Why? Because these aspects are not taken care. You have to do it in the detailed analysis as in HFSS or various software. You have to see a full analysis where this kind of phenomena is happening. So if you see, when this can happen, what happens, this is called null active pattern or zero active reflection. If this such kind of coupling is dominantly, the return loss, the particular direction, it becomes very, very poor. It goes to the one, most of the energy gets reflected. That is called scan in that direction, then particular this direction, then you are not having the radiation, you will find no gain, you will find from sometimes null. Yeah.
Sir, is this analysis can be done in specific software?
This we can very well do it in the full, any full well surveillance, either CST, you can HFSS or various software which can handle the 3D FEM or full well solving methods are available, you can do it. Any, मतलब Tigra में भी है, it can be HFSS, CST, or you have any software specific that I can tell whether it has it or not. There are many softwares can take care, but some are but you have to define it, take care by designing it. If you put entire large array, sometimes you may say that my computational capacity is not enough, large enough to solve the problem. It is indeed will happen. So those things have to be taken care. If then what happens, it's not only the low efficiency, even though if the extent problem is not to that extent serious, but its efficiency will be lower. That are another disadvantage of this if the coupling is poor. So mutual coupling in the phase array is one of the parameters that has to be seriously addressed while designing it. Scan parameters are explained and the poor envelope correction for the MIMO systems. Again, the similar correlation factor when you have multiple elements like in terrestrial communication, where the MIMO systems are there, this will have poor envelope correlation factor. So these are the various problems we have to address while designing it. Yeah. Here I have shown some of the different type of lattice structures. It can be a rectangular lattice structure, how the for different beam, how it will be looking, the scanning, what are the number of elements, what are the scan loss. If sometimes you do not have that, you will have, even though it is a circular structure, you will only select the circular aperture, but the lattice is still rectangular. You can have a triangular. Why it is not in the straight line? Because you have chosen the triangular lattice section. That is why it is shifted, laterally shifted. Next node is laterally shifted. That's why it becomes a triangular or hexagonal structure. It has its own performances limitation. The symmetry in all the planes it will not be symmetric, but it will reduce the number of elements to a certain extent in some of the various cases. So this lattice structure also to be chosen. Depending on the which particular direction in terms of phi direction you have need scan range, scan angle. Accordingly, either you choose the rectangular is the best in terms of, but it is a full dense array. If you want to reduce the number of elements and still achieve the performance, you can think of the triangular lattices. The one step further, you can go a sparse array. This is a completely sparse array, or it is called a periodic array. At least the example I showed is the sunflower type of lattice, but it is not regular, but at least having regular structure. It reduces the number of elements. It can reduce the number of elements, reduces the cost in terms of, and this kind of now technology, not the sunflower lattice, but the aperiodic array, that is becoming the topic of research and how to optimize it further by using the various methods, either AI or any, even there are various polynomial equations are also there, how to design that and get the state performance over the entire scan range. So this is the essentially trade-off has to be done a priori when you start your actual phase array. Can you go next, please? Design consideration for phase shifter, there are various different types of phase, analog or digital phase shifters. It can be either a continuous phase shifter or discrete phase shifter. There are various domains are available for this, either main phase or MMIC based phase shifters. I think somebody has taken the MMIC based topic. Whether this topic has been covered or somebody? No.
MMIC is taken by Asmita Rani.
Okay. So various nowadays phase shifters are also realized in the MMIC based phase shifters by active devices. So this can also be very miniaturized structures, and the if it is a passive, completely it can be a ferrite or it can be a directed diode or anything. The other thing also be possible. as I mentioned, the phase shifters, the major design parameter, I will not go much detail the line by line, but the major design parameter concept is simple. Either you change these two parameters. Simple is pi is 2 pi by lambda into L. Then for particular, let's say transmission line, if L is, let's say L is the is the length of the transmission line, then it will give it's a one particular phase. Now, if I convert only lambda, that will be what will happen? It will be nu by f, so that becomes f by nu. If I convert this nu, if I write it, the velocity, it will be 1 upon 1 of micro square root of mu e, that it becomes numerator. So these anyhow, these are the constant. What is the changeable is the length and this mu e. If you control this mu e, in ferrite, if you control mu, in other devices, if you control, you can very well change the phase shifter. If you change some of the lines, you change the length of the line, you will change the phase control. So how these three parameters can be tweaked with, you can achieve the phase shifter concept. So these are the various specifications you should consider while designing the phase shifter. I will not go by this. The major, one of the important parameters is what is the number of trips to the digital phase shifter, what is the number of control bits, because if let's say 5-bit phase shifter is there, then 360 total fish and 2 raised to 5 and the 32, then it becomes 11.25 degrees. The minimum phase shift you can achieve from the phase shifter, and that also will introduce a quantization type of. Even though you have element in a single element, but if the phase shifter, let's say 2-bit phase shifter, if you use, then what quantization will come? 90 degree, every 90 degree or every 180 degree only it will give. So that is the quantization is also introduced by the type of phase shifters you use, not only the sub-array, but also the type of phase shifter you use. Okay, this effect we have already studied, the, as I mentioned, this one. Yeah, so this quantization not only affects what affects not only the change in the amplitude, but also some changes to the extent of beam pointing. So that's what I was saying, the beam pointing error due to quantization. It is not it would have been simple. It also affects some kind of the dithering or the wavering of the beam pointing error. If beam is really large and it affects, sometimes you need accuracy of 0.01, 0.02 degree, then it does matter a lot while designing the to take into account. Like here I have shown the various effects of quantization, how the patterns can affect the, if it is ideal, then I should have got in particular beam is can from here to here, then I should have got only these kind of, these are the basically side lobe you are saying, because I have plotted the intensity. So ideally I should have got, if the beam is scanned here, I should have got this kind of three-dimensional pattern plotted in the sort of a two-dimensional way, UV plane. But if I go back to the, if we go to this 2-bit phase shifter, this is the worst case. Normally we will not refer that. And just to exaggerate, I have shown the effect. What will happen? Then this effect is plotted. I am not only getting the side lobe, I am getting in this direction also scan side lobes are raised. This becomes pattern shape is also changed if you see. So these are the various pattern perturbation happens when you choose the type of number of bits of the phase shifter. This just to exaggerate, I have shown if you take the 6-bit phase shifter is reasonably very good. It's only the quantization of 5.625. You will get compared to the ideal, you will find very less power is going. Beam is still very stable. So this is the similar kind of the performance you can get at some tolerable cost of this degradation. Now, what are the broad classical antenna technologies for beam reconfigurability or beam steerability? Let's say starting from the here active antenna based approach, then this we have talked in some of the cases is the either analog phase shifter or directed or ferrite. You can go the MMIC based digital phase shifter already mentioned, or beamforming ASIC. It is also the same. The only way of technology, what is the technology using, that is classifying it. The another is ferroelectric based, material based. These are the, we have done some of these aspects also. I will show some photographs. Is liquid crystal based or barium social catenary based. Lens based approaches are also there. Green graded index lens, Rodman lens, or DFB type of phase transformation. You can achieve by playing with different technology. The concept is the similar. You have to play with the amplitude and phase, or if it is only steerability, it is only phase. But how you achieve it, that's the matter, and that is the technology. These are, if you see different technologies, they are very, very different in terms of the design or in terms of realization. But concept applied at the fundamental is the same. You are playing only of the amplitude and the phase. Similarly, digital beamforming approach, this is the current or a software defined data nowadays. This is the trend is very much going on. You can take the data in the RF domain, don't put any RF phase shifter, you take it into the down convert into the digital domain, and then later date you can play with the amplitude excitation, phase excitation coefficient. You can generate any direction beam, you can play with the generate a multiple beam. This is the technology I will show you. You can generate simultaneously multiple scalable beams at very reasonable, affordable technology. This is the current need of the hour to more research or more focused work is required on this domain to develop the technology and to make it low cost. The major efforts are required to how to reduce the cost. Of course, I have not covered the mechanical steering based approach, but this is the still being reconfigured possible. Reflector surface reconfigurability, that's another approach. I will not touch upon this much. Either actuator or 3D exchange, you can play with that and you can still reconfigure. Holograph beamforming, this is also one of the trend. Some of these are still trending, this technology are trending, and more research is still going on in this direction. We'll see some of them in this future, next coming talk. Right. Yeah, now some of the antenna design for SATCOM on the move terminals. If we see the current available technology, the applications, what are the challenges? Multiple beam operation. What happens, especially the this technology why requiring for LEO. Well, let's say you are at Nagpur and you want to use this, let's say, Starlink communication. What happens? The as I mentioned, the LEO is going within 10 to 50 meters from horizon to horizon, and let's say you have tracked one satellite right now and started communication, which is coming from the horizon, and I continuously track the satellite. But the moment this goes this side, another satellite by the time before that, the another satellite is coming. If I miss this, there will be breakage in the communication. I have to do the again, come back to this. If this avoid this kind of thing, there is simultaneously two beams to be essentially required to track this. What happens if I generate two beams? Either it's a conventional approach have the two reflectors. One satellite is one antenna in the ground also they are using the two antenna approach. The one that mechanical steering one satellite, other is for other satellite, which is rising. Another is sunset or the setting towards the horizon. So in order to that, if I want a single antenna system, then the digital beamforming or some other approach as I mentioned, they can generate simultaneously multiple beams and from the single aperture, which is can be scalable independently. And that is the essentially very much required for this SATCOM on the move for communicating, tracking with this low Earth orbit satellite or even various radars are there. The defense radar, or even we have when we launch the satellite, the rocket, it splits into huge object falls into the sea ocean. We have to track those orbits. We need a multiple object tracking radar. There also we need that technology. So these are the applications where essentially required the simultaneously steerable multiple beams, which is very effectively possible into the digital beamforming approach. That is the still, but there is a lot of work or a lot of miniaturization or cost reduction is required in terms of the IC development. So of course, the currently most popular are some of the mechanical steering are still get the business largely because it's a relatively low cost. Now, if I suppose go to the aircraft, I have to have the dome size has to reduce. What is that? Is very approach is the breaking the array. I will show some slides probably available in my presentation. That is a concept is used 1D scanning in that. Another is the approach which I showed the phase array approach. And these are the 10 things that are still going on. Various applications are for the SATCOM on the move are being done. So this sub-array based for now I've showed some of the practical examples, some of the things which are done. We have done that I'll be showing it. Some of the some cases I wherever I referred, I will refer in the footnote which paper I have referred or which company have developed this. So these are the of course the simple the sub-array. What are the elements are there into this? And the concept here, of course, the small, the element, the array size was small, where I can afford the, for lower scan angle, I can use the larger subarray, as I mentioned. And when the requirement was my small, we use this, subarray based approach with a lesser number of, let's say, even 3 by 3 subarrays configured for the material that microscope patch element as a radiating element, and we could do this, over the large bandwidth and achieve the over the wide frequency band of 10.5, 12.5, and the respectively scan angle was more less than around 10 or 15 degrees. So this is the radiating patch. Again, there will be a stack patch to improve the bandwidth. This is the one approach is being very much you enhance the bandwidth approach. You might have some might have people have designed it. These are the again to increase the various layers, how the different layers are put into that, increase the bandwidth, increase the coupling. Because many times what happens, the even generating laying on this fluid also has a problem. So we have to have the either EM coupling or direct coupling. I'm not sure whether it has been aware of it, you have been taught or you have been studied. But that becomes a challenge, and so it becomes a stacked patch array is a very much important parameter in the designing of the radiating structures. Yeah, this is the concept which I was showing, where you have a if suppose I wanted a full array, what would I then you assume these are the 1, 2, let's say these are the 8 elements are there, 24 are there, 24 on this. Let's say this is the 12 subarray. Then I would have got this much height of the array. Then if you put it on the aircraft or anything, you would have needed this kind of height to have a completely the dome set. But in order to avoid that, what you need, what you divided, you split that, broke into the 12 linear array. Now, this concept again is same. Here, if you say I have broken this into these different layers, what happens? In such a way that each radiation path is not blocked. Each radiation path is not blocked. It is getting, you are still having. So now you have to play with again the distance such that for different scan angles, you have to really change by the designing, changing the distance, adjust the phase, so that when they come in the phase, final phase front, in the phase front of this, they will come, all will come in phase. That is essentially required. So this is concept is only to this technology is only to reduce the height, but complexity introduced in terms of design is to have the different way of achieving this. The mathematics timing you just forget about, but it has reduced the volume because that was the practical constraint for designing it. So this is the fixed beam low profile array. Here you can steer electronically one direction, rest is you can still achieve the mechanical. So many times this kind of concept is very important. You can steer azimuthally in the mechanically or elevation electronically. You will save the large number of. Had it been if I use the completely electronically steered beam, what would I have required? I would have required 12 by 24 as a number of active elements. But if I doing this, I needed only the 12 subarrays, as like this 12 are there, only 12 active modules are enough to beam steering. But what I lose, I will not get the electronical beam in the azimuth plane. I will use the mechanical rotation in the azimuth plane and do it. So it is not causing to my volume change. Had it been this entire elevation wise, I have to rotate this way, then it requires a larger height. Larger volume. So those are the practical design constraints, practical challenges, and such kind of constraint or design constraint are only giving the need of finding a different solution. And that is why this kind of solution come into the picture. And you have now, you have sacrificed, you have reduced the height by combining both mechanical scanning and electronic scanning. You have reduced the cost by having only the 12 subarray active modules. Can you go next? So these are one of our radar imaging satellite antenna, RSat 1A. This is the again a full phase array. Here also we did a sub array. What is the sub array? What we did? When there are 588, there are not 288. This one linear sub array we use is around this 1 meter type. There are 24 in this direction, and then there are 12 such types. So there are 288 modules are there. The radiation patch, microstrip patch, if you see, it was also unique at the time, giving the very good bandwidth and very good efficiency, having the both polarization, horizontal as well as vertical polarization. Having one is by EM coupling, other is by aperture coupling. That way, this coupling was achieved. I'm not going much detail in there because of yeah. So we can have the full bandwidth in single radiating aperture. We can achieve both the polarization and over a wide beam. Then these are the various modes of radars are shown, whether in the sleep map mode or the scan mode. These are the various. This is the path of the satellite and shown the where we need a scanning of beams for different modes of operation. Sometimes what we do here in the radar, we have a spot beam, then we will use the entire array for generating beam. If I need a larger swath, larger coverage, larger image I have to replace, then I don't need the mount, I have to use the smaller size. Then it is commandable from the ground, we use the smaller size of the array, and then we'll get the wider beam and we'll get the wider swath of the beam. So these are the various ways achieved. This is about one of the really unique example of very 6 by 2 meter antenna radiating active phase array which we are using in one of the. This is the satellite which is put in the testing in the compact antenna test range. Is showing during the photograph is of that. These are the various basic block elements: phase shifter, amplifier, variable attenuator, amplifier, variable phase shifter, amplifier, and predictable. This is the basic element. These are actually MMIC modules are designed and integrated into LTCC package. LTCC low temperature profile ceramic packages. They are put into that and small packages. And this kind of air activator. Another example for geo imaging satellites. One satellite was failed during the launch itself. Our launch vehicle was failed. The satellite was Session11. Now we are launching the satellite within the next 2 months. This is called GSAT2, geo imaging satellite. These are the mostly for the strategic users. They use this kind of application with very high resolution images. And again, this is from LEO and this is from GEO. Then what we need is here as I mentioned, sub-array size. We have used 3 by 3 sub-array. I reduced the number of active elements. Here, in one direction, in one plane, there was scanning was not required, so I used the linear array as a sub-array. But I needed nearly 588 modules. Here, I needed only 64 modules, but gain was also very high. But the scan angle was also less in this or more in this case because this is from geo satellite. So this is the one of the phase array which has been already grown and now again will be going in next 2 months. In both images. Yeah, these are the various photographs of various different stages. This is the backside electronics. This is the electronics of the TR model. These are the block elements shown here. SSP driver and current antenna. These are the elements are shown. This is tile by tile or the panel by panel shown. Their specification not going into detail. Yeah, another future scalable antenna because the mass is also onboard satellite antenna mass. This is not developed by us. I just put it. But this is the technology what is required and still not so mature, not even worldwide also. But it is essentially required. What happens if you go with the solid patch array or solid disk substrate? Mass is significant. What we need is a membrane base. You see, this is the single membrane base. Membrane only the patch is printed and membrane was really thin of order 100 micron or so. And there the electronics are also integrated on the back side of it. So the technology in terms of not in the antenna design but in terms of the process, various processes are required to be developed here. Those are becomes essentially in terms of the technological element. So as I mentioned, again, how you achieve it, how you do it, what are processes involved that makes the crux in the technological, the different types of achieving this phase array. So this is membrane-based steerable antenna for geostar application. We have developed one membrane antenna for our Venus application and we'll show one photograph at the end. I will show just. We go next. Yeah, now another concept is very much, I will mention one of the classification was holography-based approach for using for beam steerable or beam reconfigurable or shaping beam anything. The concept is here is like our desktop, whatever we have it as a LCD panel. in that LCD panel, if you change there is a literally liquid is filled between the two glasses, which is playing the of the in the or LCD panel of PC display. It is playing only with the optical holography, but in the microwave we have done so that was really innovative. One of the things we have used this concept in the microwave domain and achieved the beam reconfigurability. Here, what happens? The concept is simple. When the two substrates, there are two electrodes are there, and these electrodes are controlled by the thin film transistors are there that we printed in the nanoflexible electronic center, and there are very small transistors. The moment you apply the voltages, this unidirectional the crystals they becomes oriented in this way, and then it gives that effectively changes the dielectric constant. The capacitance is nothing but the in the macro domain. What is if you change the epsilon, effectively it changes the capacitance, and the phase shifter, as I mentioned earlier, you play with the epsilon, you will be able to achieve the phase shift. The concept is used. I'm not going in detail, but if you change the epsilon here, you use the property of this liquid crystal as an anisotropic property, and you are changing the voltage, applying differently, and you are able to change the capacitance, and effectively means capacitance means you are able to change the phase shift, and you are able to change the steering or beam configurability you are able to achieve. The major element, various techniques are there. Meta surface is the synthesis-based techniques. Holograms are essentially required. Liquid crystals and thin film transistors are essentially required. These things are able to achieve it in. If you can fabricate it, this will be really a game changer. Can you go this thing? Yeah. Now this holography approach is a simple concept. It is the optics concept of optics in the physics you have studied. If you have two waves, one is object waves and is a reference wave. If you make this object wave and reference in such a way that the hologram is desired hologram is formed, then you can generate a beam in particular direction. You can steer the beam in particular direction. For example, I've shown here if this in this how this reference wave is generated. Reference wave generated in the, let's say this is a simple patch there where the different relating elements is not the macroscopic patch, but they are the complementary material elements. These are basically the electric resonators pattern into the waveguides structure. It can be a rectangular waveguide or it can be a surface waveguide. I've shown here is let's say surface waveguide. I put the single point feeding technique. Then the spherical waves are generated in this the dielectric substrate and generates these circular spherical waves in this dielectric slab. Then in particular direction, if you need it the particular direction, then this, if let's say I've shown here the hologram for 10 degree beam scan, the phase will be the incident wave at 10 degree will be look like this. If you have generate the interference hologram pattern addition of these two, you will get this kind of pattern. So effectively, if you see the how this is instead of the original thing, you are getting the different. For example, 60-degree beam scan, instead of looking hologram looking like this circle, it will look like this, the interference pattern. This is on the basically this will be you can assume this is the aperture field distribution on the your radiating aperture and able to generate. Now you are able to generate this steer the beam, reconfigure or shape the beam, anything you can play with. This we can generate within the liquid crystal or even the other various techniques are also available. Very good. Again the hologram based approach. Here I have shown the simple example which I mentioned earlier. The plane wave, object wave and reference wave. Let's say this is the reference wave but this and the object wave which is coming from the different direction. How this can be hologram can be generated in the waves and accordingly how the radiation pattern is getting scanned. So this kind of the simulation I have shown here. So this is the concept which is applied for the holography based approach for the beam. Here now effectively I don't need a phase shifter. I don't need any other element to be added. Now by in the geometry itself I am able to generate a hologram and able to scan the beam. These are the, of course, the design of meta elements. I will, if you, not go into detail, but the simple measure flow is again, there are no direct design techniques are available in the paper, but we have to work a lot of mathematics and arrive at some of our own tools. And then first is simulation of unit cell, that is called electric resonator or complementary electric CEC. The extraction of its S parameters from the various tools, either HFSS or anything CSTM tool. You have to have your own MATLAB code. Then computation of polarizability from S parameter matrix, then apply the Lorentz constant hologram, and then finally fit it into the hologram distribution and then compute it. This single software doesn't do this. We have to have our own tool to synthesize or the design this. But the result is really amazing. Yeah, now I have just shown the explorer view of what I have told you, the liquid crystal base our antenna, which are basically the hologram based beam steerable. Here the radiating structure is on this side. Now assume that the radiation is happening on the bottom side. Let's say this is the T10 waveguide mode. On that, we have created various slots. Let's assume currently the uniform linear parallel. The single element is like this. It is called a meta element. What we have done is this is the thin film transistor having the dimensions of few micrometers, few microns. It is basically a gate FET device which we have printed on the substrate. And it's a gate line and connected accordingly. And the moment you change the drain voltages, what happens? Here it is shown the thickness, though it is exploded too much, the thickness is only the less than, if you see the dimension, how their dimensions are coming. The entire this to this thickness is hardly 1 mm or 2 mm or 1.5 mm. That much only this will happen. So these are here is only the realization technology does play a lot. Basically, it's like a display panel either on mobile or on the computer display monitor. Here is the only 50 to 100 micron is the liquid. This is literally in terms of the liquid. It is the specific material is liquid crystal material, that is the EP 507 or some. There are some grades are available which can be having anisotropic properties, and then they are put it into these are the spacers of the dielectric spacer, because maintaining the 50 micron thickness uniformity is really technologically challenged. And then there is a passivation there, and this is the electrode thickness, and then you can have this completely transistor. The moment this is having the thick order of, you see the dimensions are order of nanometers, though it is showing in the few centimeters, it is in the nanometers. Each element wise it is placed here. The moment you change the voltages, you will get the equivalent circuit is shown here. It's called single pixel. The changes the voltages, you will be able to change the capacitance, effectively the capacity of phase. Can you go to the next one? Yeah, here the shown here, like what we have made is a planar array. And then this is the substrate integrated waveguide. We have the elements, these elements having the different connected line, DC bias lines, and then we are able to changing the voltages by through a controller, digital controller. We can steer the beam. This is a field and speed distribution I have shown along how it is happening, and these are some major performances of the realized gain of the liquid crystal based meta surface center. This is a really unique way of finding pattern on that part. Yeah, these are the actually developed hardware. It's just thickness of 2 mm or 2.3 mm, and this is the completely the lines are also not wires. These are just the simple few micron, 100 micron thick bus structure, and able to control this entire large number of elements and able to. Here, the reconfigure. This is one of the very good technology has come out. Only worldwide, I think there is one company which is Kymeta is generating able to produce this really commercial antenna. Really is a marvelous piece. We have just developed just few prototypes because what we are lacking is the fab facilities. These are the fab facilities are essentially required, like whatever the large TVs or panels they are fabricating. Such kind of facilities are required, and in India such things are not fabricating. We have only at IIT Kanpur one small manufactured electronics. They are able to. That's only 100 by 100 or 150 by 150 wafer. With that, we developed this kind of concept and developed this antenna. It was really a very good uh, technology in terms of having the phase array or scalable array without using any extra array. This will be very cost effective. Yeah, again, these are some of the photos in the development status are shown how these lines are there, and how all this measurement during the measurements, what are the things required. I will not go into the detail. If you have any question, you can ask on the explain. So these are again the development during the how this whether the what are the tricky area where we fail. As I mentioned in the many earlier also for a as a spacecraft, what happens? The whatever I am showing, they have not gone the one pass success. We have failed many times. We have, but each failure was giving us new learning and able to improve our knowledge, improve our skill, and yeah. Because that's the basically the process of learning it. In that part also, the concept, some many times concept appears very straightforward, very simple, but the moment you start realizing it, there are the various practical aspects, practical failures will teach you what you have missed in the design. Those are very important. Is apart from the rather I will say the design part will be the 20%, the rest 80% is the development side. Even if you say I can design this, yes, I can agree to that. If you say I can develop it, I have to take it with a pinch of salt because it's not only you can do it alone, it's a multidisciplinary. You need a mechanical engineer, you need very semiconductor fab facility engineer, you need all of various process engineer, vacuum engineer, you name it, it is required. Because what I showed you that is the 100, if I go to the previous, just one more previous. We failed completely 1 year achieving this thickness of 50 to 100 micron uniform over the side, on this side. What happened is that though we conceptually we thought it was very simple. Okay, I will put the small spheres, mix it in liquid, and I will be able to get this uniform thickness of 50 to 100 microns over the entire. But it didn't work. What happened the moment this is the liquid, when we are sealing it, there will be some pocket. Probably you might have seen if you feel it, even अगर हम जब मोबाइल चोर अपन जेव्हा हे लावतो आपला टपन find bubbles, air bubbles, then the person do it with the pressure and try to remove the bubble. It appears irritating for viewers, but in this case, the performance is completely wrong. That kind of air bubble, it happens in anywhere in the aperture. We are not getting the scanning, we are not getting this control voltages. That we struggled nearly more than 1.5 years, despite putting all the brains together, mechanical engineer, process engineer, and all. But we could not. Then there are various. Here only when people file the patents and they don't disclose this. If I say disclose this, I'm not disclosing anything, even if I disclose it here. But the trick of the matter, which I'm not telling it here, how did we achieve arrest this kind of problem? And nobody tells it even in the patent. How I arrested this uniformity, how I arrested avoiding the bubbles into that, because I cannot put the pressure in that because it's not so easy. Having these 50 microns thick gap is difficult to visualize also, even despite the, and that whether it, and this becomes a very sensitive design. Even if it becomes 50, I've just shown the broader range. I have not put the exact number. Let's say 50 micron is the only number. If it changes by 10 microns or 15 microns, the performance is, if it is starting from the 20 to 21 gigahertz is the intended band, it becomes 18 gigahertz. Then the whole development goes waste because that is not used for it. These are I'm just telling you one example how this the technological conceptually it appears simple sometimes, but the realization part is the key in the success of the development. So these are the, we learn many things. मतलब it appears, oh, we missed this physics, simple physics, but when we applied also simple physics, then some other parameters came. ऐसे करते आम्हाला भरपूर काही शिकायला मिळालं, पण ते हेच लागलं शहाणपणी तेच आपल्याला नंतर शिकवले. तसंच झालं आम्हाला भरपूर गोष्टी. Many times we miss it. Otherwise, conceptually on paper, it's simple. It's just we have to do it. We'll be able to do it. Sealing also is a problem. Many small things which are taught. Just example. Just one thing. There are other aspects also. I'm not going into detail. Next. Yeah. Yeah. So observing where is the crux, where is the error, we have to really find out in a lot of microscopically. These are, I'm showing microscopical picture, how the uniformity is there, and how it is changing the its voltage to capacitance varying. That also we have to calculate. Different setup is required to be established on that part. And then once we get it up, then we have to have a probing whether it is really giving the intended aperture or intended variability. All things are required to be essentially done. As I mentioned, I still hold that the 20% is your design on the simulation, but 80% is on the development efforts are very much essential for successful of any of these technologically state of the art. Okay, here I have just shown the procedure. Maybe I'm giving you slide. You can read it. These are the various ways of doing it in the designing. Designing also is not straightforward. No paper will give a single design. How to design it, and how to, you have to have your own software. You have to use of multiple software. You have to use it. Even neither of the HFSS nor CST will give entire design. You have to extract the parameter from solving it in HFSS, extract it, put it MATLAB calculation, again use it, again feedback to the software. And those kind of things is essentially required to the process. And then only you will be able to design it. But design, as I mentioned, again, it's not a foolproof. It's only 20%. Rest again struggle is in the development. So we achieved in the development some scanning of the beams by changing the voltage. If you see my phase array only is just thick like our display panel, like mobile panel ka utna hi thick 2 mm ka, and I avoid all the phase shifter and anything, and the beam was able to scan it, reconfigure it. Yeah, these are some of the different photographs during the development stage. Yeah, then the one of this simple, the spin-off from this. This was the liquid crystal based, as I mentioned earlier, this antenna. The spin-off became in the holography based patch antenna, holography based planar antenna. This was a very ultra thin. Means you don't, as you are studying the array, you need a feeding network to cover all the length. Here, I don't need any feeding network. I will give a 31 dB or even higher gain by a single 1-point feeding. No feeding network, no printing, nothing. Just use the concept of holography. As a previous slide I have shown there, some of the design concept. Surface wave excitation, single point feeding. This is the only single coaxial line. And this technology design wise cheaper, but realization design wise difficult, but realization wise very cheap. Is what you need is only single PCB with a single connector. Once you design it, you have got this we have developed at 20 gigahertz and 30 gigahertz, and single PCB of 1.2 m thick. There are more than few thousands of elements are there, meta elements. Meta elements are sub-wavelength sizes. They are not lambda by 2 as you design in microstrip patches. There are the sub-wavelength which is shown in the earlier in this slide. There was the element. Those are sub-wavelength sizes. And the only what is required is photogram in such a way that sub-wavelength means what? Sub-wavelength, can you go back previous. Normally, if I design a single patch, what will happen is you choose a lambda by 2 or anything. Okay. And if you go with the lesser than that, the patch will not radiate. Okay. So what we have gone into is that since I have to generate a hologram, I have to have a small pixelization. Then this size of the element is, when I'm saying sub-wavelength, wavelength में multiple टुकड़े में है, मतलब it is of the order of 0.2 lambda. Okay. मतलब 1 lambda में 4 या 5 element है. तो इसलिए sub-wavelength बोल रहा हूँ. Size of this element is sub-wavelength, that is 0.2 lambda or even less, around that.
0.2.
मतलब approximately you can take it to 0.2 lambda. Okay. Sub-wavelength. But now what happens? Suppose let's say, can go back to the previous slide. The next slide, next to me. Go. Go. Yeah. Now, if I do this, I have to generate the entire hologram. Yeah, इसको escape कर लीजिए, presentation से escape कीजिए, presentation से escape. Yeah, this was the hologram. The concept was based on this, whatever antenna I'm showing. I have to generate, let's say scanning. Let's say I'm generating a fixed beat. When I need this kind of pattern to be required to be generated. Then this is, if I have to element, if I take it coarse, then there will be large quantization. I have to have really small pixelization over this entire aperture. So that is why we are using a small size, bare minimum which is possible and which is radiating. So that is called the CEC element design, that is complementary electric resonator. Those are designed and placed in such a way that so that whatever the radio hologram we can generate, we are requiring, we can quantize it or discretize it in a very small sizes. Then only very good hologram will be represented by the actual element, and then pattern will come. If I have the lambda by 2 size element, hologram will be still possible, but the element discretization is so coarse, I will not get the pattern as desired. So since like आपने कभी पिक्चर देखा होगा, आपने स्क्रीन का रिजोल्यूशन के लिए आपने बोलते हो I need a 4004K or something, then you will get a very good quality. Similar here, unless I have got the very small size of the pixel of the radiating element, then only I can capture the electric field into aperture. That is why I need sub-wavelength size of radiating element. So this way, this was the two radiating aperture were generated, and we got very good high gain and with a 32.9 dBi gain. If I want to have this much kind of gain with a single fixed static patch array antenna, I will be requiring, even if I go with the microstrip patch array, my efficiency will be less than 30%. Even 30% I am saying very conservatively, it will be less, because the number of element will be very large. If I simply say this is, if it is roughly 30 lambda by 30 lambda size, there will be 60, how many, 30 lambda by 2, 60 by 60, there will be more than 2000 or something elements will be there, and the feeding network, if you imagine, that will be too lossy and too efficiency will not get, unless you make it in the waveguide feeding network, and that will be bulky. But that is, in this concept, I'm just putting in the single field as a coaxial connector. If you have seen at this point, then it is generating a spherical wave into that, and then hologram pattern is designed in such a way that we are able to get very nice Gaussian beam with high gain and high efficiency. And this is the very good, very cost effective in terms of the. So here, with respect compared to this technology, sometimes that's why, as I said, cost is a driving factor many times. Then I will put this on the mechanical scanning antenna. People will prefer this other than phasor because there is no cost involved in it. Yeah. This is another way of doing it. This is not ours. This is a German company. They were also trying this. The concept is different, but they were putting the phase shifters in the liquid crystal. We are able to have the entire aperture on the face directly. They are having each patch के पीछे phase shifter बना रहे हैं, say हमने different pockets में. That way they have made it. Ours is a contiguous liquid crystal and we generating the patch. So ours was also unique in terms of the development. There, since the papers are also recent, very not old. The technology is hampered development by the fab facility. We contacted with the fabrication facility display monitor. They said unless you give us the right to fabricate and sell that, then only we will fabricate for you. They don't want to just take the non-recurring charges. They didn't accept that. They want you give us your rights, you give right to us, we'll fabricate and we'll sell. We'll take the business. The business rights will be ours. But that kind of provision was not provided by our ISRO, so we did not went into that. But there are what we are lacking in some terms of very good fab facility. Probably in the near future, if the good fab facility coming in India, if they take it up, we'll be able to scale it up and develop those kind of antennas. That is reconfigurable. But fixed beam, what I showed in the earlier slide, that is anyhow people are using it. But the way we have given technology transfer to the Indian industry, they are able to take it and manufacture. Like Bell has taken this technology from us, and they will manufacture it and they will sell it at low cost. Because our ISRO's objective is not for business; it is for the benefit of the society. So we are not profit earning. We want that if an Indian company is earning, that is very fine for the benefit of the Indian society. Yeah, this is again a very simple concept of directed diode were used. The pin diode was used for the scanning the. There was one of the satellite VSAT 6 and now we are sending 32. This is in S band. What happens is that earlier otherwise single element was good enough to the satellite is having a large 6-meter unfoldable antenna on board, but it is having the problem of in S band lot of terrestrial interference is coming, like this LTE and mobile communication. They are interfering with this satellite spectrum, and in order to increase this, reduce the suppression, what we need is essentially slightly bigger array, scanning array, but these are carried by the defense soldier. They don't want a bigger array, they don't want, but the spectrum interference is so large, they have to have this kind of slightly bigger, but if the moment we get the bigger array, it will become difficult to point toward the satellite. So we need a phase array. And again, since that is required in the soldier is carrying if it is taking large power and large power means it essentially requires a battery. It goes in field, it doesn't have power, it has to be have on the back. Then it should be consuming less DC power. As I mentioned earlier, what matters is what is the requirement, what is the application. Here, the DC power consumption was less, essentially for the given constraint. Scanning was required to automatically track the satellite. And the low cost was anyhow, it was important, but that was not determined by the different forces. So we tried with this concept of having the only pin diode simply, statically, no much DC power is required, and able to scan the beam. So it is very simple. Again, we use the concept of meta element, meta surface. We use the pin diodes and we use the binary scale photography, and we are able to scan automatically. Here again, the technology is within the reach. We are not requiring big hardware or big fabrication facility like display, but here we have put the pin diodes. We could achieve the steerability as shown here, and the cost is also low, and the mass is also very small, single PCB. So the soldiers of these they are able to, they can make use of it with a very light weight. Another one of the application for our future scatometer payload. The current scatometer payload is what is basically it is scanning the beam. This payload satellite called StatSat or OceanSat, which is getting the ocean winds, and the application of this satellite is the generation of find out the genesis of cyclones. Because cyclones यायच्या काही दिवस आधीच जे फॉर्मेशन होते त्यांना कळून आणि त्याचं इन्फॉर्मेशन घेण्यासाठी हे जे सेन्सर याचं मायक्रोवेव्ह रिमोट सेन्सिंग सेन्सर आणि ऑप्टिकल रिमोट सेन्सिंगची गरज आहे त्याच्यातला हा एक आहे इम्पॉर्टंट मायक्रोवेव्ह स्पेक्ट्रोमीटर. ऑप्टिकल सेन्सर मी बोलत नाही कारण की मी या आपल्या डोमेन मायक्रोवेव्ह साठी बोलतो. हा वन ऑफ दिस पॅरामीटर इट विल गिव्ह अ सी surface height, see surface waves height, its direction, surface wind direction, it can be derived from this spectrometer field. In that, what is the requirement is this from the let's say hardware point of view? It is the satellite is going. It is required to scan the two beams continuously in a conical manner and move ahead. That way, satellite is going let's say forward direction by having beam and scanning the entire beam. These two beams are continuously scanning and going. So the entire region will get scanned while the spacecraft is moved in the velocity direction. Now, the technology which we use is flown is this, is mechanically scanned. What is required? Right now it is scattering the serving the purpose. We have flown 3 such satellites. But what our quest for the developing the technology with low profile, what we are proposing is, rather this requires a lot of hardware also, the huge rotary joint, mechanical scan mechanism, and its inertia, which create difficulty for the spacecraft design. This is the spacecraft bus. This is nearly 1.4 meter diameter, it's big size. If you want to demo this, is also required a lot of complexity structures involved into the idle mass also to the satellite. What proposing an alternate technology is vector-based electronically beam scanning antenna. Here, the concept we are applying is the basically. I will go to the next slide. Yeah, the concept is applied is the. The concept what we are using it is simple. Instead of reflector, we are using a planar reflect array. The planar reflect array, again, it is ultimately I needed high gain antenna, reflector is the best option. Otherwise, if I go with the planar array, I have to go with the huge feeder network. That's again costly and difficult, challenging. So we went for the reflect array. Instead of curved parabola, we made it as a flat. This is a flat substrate of dielectric 1 mm or 1.5 mm thick. Shown here is because of the backup structure. Now the print on this area on the patches are such designed that they will compensate for its curvature and make the face front planar, plane wave front, like what the reflector property does, parabolic reflector property does. Now this is for a static one. What we did is we put it there, a varictor diode. Let's say this is a single element. There we put the varictor diode with the stuff. Then we change the voltage of the varictor diode, vary the varictor diode, it will change its capacitor, the property of the varictor, and you are able to change the phase on this aperture. Again the same, then we are able to scan the beam. Like I have shown the scan drop. Of course, the large scan angle, there is a gain drop. Since we wanted to up to this range, we are able to absorb this. It's not as ideal as the mechanical scanning where you do the scan, there is no scan loss. But here it is serving the purpose. It is giving the simple scanning. Now if you go with the previous one. Yeah, this beam was reportedly scanned only at next. Yeah. If I go, I'm having only single reflect array like this, and I'm able to changing the electric control wise, controller changing the voltage. I'm able to scan the beam as is showing in the circular fashion. And over and above that, but the moment what happens, just introduce here some of the blocks. I'm not going into much detail with the discussion on that. It requires the large number of elements. Essentially, then it will call for all these control lines. If you are digital engineers, probably you know that those many analog voltages controlling, it becomes a huge controller. Controller also will be challenging. So what we did it further is periodically crystal reflector. We designed so that we can reduce significantly the number of control side load, but here there will be increased side load, but it is tolerable. I am able to see a periodically clustered reflect array antenna, and with that I have avoided the mechanical steering, but able to scan the beam, reduce the number of hardware complexity on the controller by using the periods. As I mentioned in one of the slides, like the sunflower array, our periodicity is really making the entry into the antenna array domain. It is giving advantage. Of course, at some penalty. Nothing comes free of cost. It is having this kind of undesigned performance. But if it is tolerable, you are able to go with the reducing hardware. This kind of development, we have done it, and some hardware we have made it, prototype we are going on. Okay, this is not ours, I am not showing this over. This is again, just for the completeness sake, this is a periodic based approach for beam steering using barium strontium category. Once we did that, but we failed in that, probably the material property we could not achieve properly. As I mentioned again, multidisciplinary, really we need material science scientists also expert also. There only they will be able to play with the material and they use its expert property for the application of it. This is shown as a good working example. Somehow we could not achieve. Again, there are barium strontium material is used. Change the voltages. It will change the again the these phases here as a property of periodic material. These are used and achieve the again the scanning by changing the aperture phase. Yeah, these are just previous one. These are I have shown the example like as I mentioned. These are now MMIC based or ASIC based application specific IC. Now, earlier when there were like what we showed into the array set, that photograph shown whether it is radar emitting satellite or GSAT, there were these DR models were not in. There were MMICs, but they were packaged in some big box package. Though it was LTCC that time, it's still cutting edge. But further, with the advance, there are multiple beamforming channels like phase shifters, variable attenuator, amplifier. This comes into the single, not only single channel, multiple channel. Let's say 8 channels will come in a single IC of size of 4 mm by 4 mm. That kind of miniaturization happened because of the advancement of 5G and mass production and the cost is also. So that we use that and we develop one antenna for the ground SATCOM on the MOO type of antenna. So this is just I am showing 2 by 8 array. These are the radiating structure. It is a multi-layer board. Can you go? I will show that. This is a multi-layer board. This is having just thickness of 2 mm, less than 2 mm. The first 4 layers is causing the serving the purpose of multi-layer slot radiators. There will be a multiple. This really involves the simulation is very intensive designs. With that we could make this into the multi-layer stack patch array radiating structures, and then again the feeding ICs are put on the bottom layer, that is on the 12th or 16th layer depending on the here for this example 12 layer circuit. The application specific ICs are here. Now power is to feed to this layer. So their feeding network, combining network is on the intermediate layer, and the DC control lines of ICs are here. So this completely board design. I have just explored what kind of different layers are doing. For this, what we need different types of analysis scale is the signal integrated analysis, power integrated analysis for it, because mixed signal analysis is another domain where you have a lot of practical challenges. I will just show one example what problem we face again in one of our failure. We made this antenna, it was beautifully fabricated, everything went fine. We got the performance, we got the scanning. The moment we saw the G by T, it was 3 dB less. We were shocked why it is 3 dB less, the beam performance is excluded. Then we found that there is a coupling, power coupling, not power coupling, there are the stability issues. Sorry, the feeding network, yeah, this kind of feeding network, here if you see, if these lines, the size is actually very small. If these line layouts are not properly designed, the power is coupled between these two these or multiple ports, then and then it is getting feeding back to the another channel, because in this IC, the IC per se is having the 8 channels. What happens to that? Then whatever power coupled is going back to the another input of another channel and getting magnified, and then will become next oscillations. And with that oscillation, it was giving, it was taking away power, and the gain was reduced, and effectively our G by T got reduced by the by 3 dB, because the power, the oscillation, the frequency were out of band, much out of band, like 2 gigahertz or 3 gigahertz out of band, and there we are getting the signals. It is taking undesired band, and so our desired power was going into that region, and we got the less gain. It took a lot of time to diagnose to us, because entire structure in simulation is hardly difficult. We have to just apply the concept where we have went wrong. After rigorous brainstorming, then we find out this probably this could be reason, we attacked it and then overcame it. So now, then subsequently, we could really develop further next time hardware, and we could resolve the problem. So what I'm trying to say is, the again, development cycle, we have to really test this, your concept, your practical approach, your theoretical concept, what are the possibilities of failure. Those things are essentially required to address while designing. Those are very important to make the product or hardware successful. Yeah, these are again different layers I just mentioned.
Sir, to solve those issues, what changes are done in layout?
Yeah. Then what we did it, we solved the eigenmode, we did the eigenmode analysis, and we solved where, what structure, at what frequency it is resonating. And this was one, we found it was nearby our band. We tried to shift that band resonating, because when we serve eigenmode, we have to see on what box, even not the radiative structure, entire cavity on which the card is put. Those things we have to solve it in the HFSS. Eigenmode analysis, we call it. There we do not driven mode, it is eigenmode. So those eigenmodes are kept much away from the frequency band. And secondly, the layout we saw, the coupling what we thought is giving 25 dB between port to port was not sufficient. We made it to the 45 to 50 dB, because the power which is coupled, which is getting nearly 15 to 20 dB gain of that IC, which is having the LNA or amplifier. So what is happening? Even though we are giving, let's say we are otherwise reasonably, but 25 dB coupling is good number. That was our one error happened there. Conventionally, had it not been coupled back, it would have worked fine. But since it is back coupled and got the 15-20 dB active gain, then effectively we got only very less coupling. What we assumed is 25 dB, what becomes 5 to 10 dB, then that is not sufficient. Then we purposely designed the layout such that we got 45 to 50 dB by between the CPW line to CPW line of different ports, by slightly making away, taking even the length of that line which are shown, that those are also to be seen whether they are resonant in that lambda. If it is not there, if it is there, then we'll find it that itself is resonating, and we will get coupled power into that. So those aspects we one by one isolated, then increase the coupling between 45 to 50 dB, then effectively 25-30 dB, even though there is active gain, it did not affect. Eigenmode, we found that we kept away from that, and then subsequently no oscillations were. Another aspect which I mentioned, the stability analysis of also to be required to be done, that we had missed into our flow chart, design flow chart, that we now made it as a mandatory part. And after doing that also, the stability of entire structure is stable or not, is oscillating or not, that also requires spatial analysis. That doesn't HFSS or CST will not solve it. We'll have to do it again on the areas or something to do and carry out. Then we found, after doing all these various areas where it can fail, then we solved one by one in the design level, fabricated it, and it completely went wrong. Yeah, then again, part of the analysis where we have to see that whether the signal integrated, because if, as we say, in the mix signal cards, but what is essentially required, you have to see that digital signals and microwave signals, if they're coupled, then it can make a havoc, create a havoc. Those things which have to essentially take care by getting rigorous signal integrity analysis, see that whether the clock is cycled, but otherwise, what will happen if the clock is giving more performance than what the channel you have selected or what the state of phase shifter you are given, which will not activate that, it will activate some other state, and you will get different phase, and you will find instead of being pointing here, it is pointing there. So this kind of integrity, signal integrity analysis, especially in the mixed signal board, where it is having RF signal as well as the digital signal, it is very, very critical. So it is essentially required to be performed. So once this analysis is done, then only ready for the global analysis, user manufacturer friendly, design for manufacturing. These routes all to be followed, and then the card is relieved global points for the fabrication. Yeah, okay. These are how the different structure. I've just shown the exhibit how these different aspects also play different style histogram play, because where we have put histogram play for mounting the different digital circuit elements, controller elements, whether it affects the RF information parameter, that also is required to be seen essentially. Those aspects trying to be addressed into or had to be addressed during the design stage itself. Again, these are the similar hardware, same things. What are the different stages I am showing here? We got the beam scan performance, different gain variation, beam scanning performance. We got good near field scanning. We do it in the planar near field so that we know that whether how the aperture amplitude and phase distribution is plotted. These are the hologram on the using the measured near field pattern. Then we know where the problem is, where how you attack. Those things can be easily diagnosed. These are the now those are shown bigger. Now these are the bigger boards. Bigger boards are accordingly taken and they are fabricated now. Which are the testing right now. Again, the low profile analog phase shifter. It can be designed as one of the techniques which can be go for the ferrite phase shifter, but ferrite phase shifter, the planar phase shifter are also possible. Like we call it as a reflection type phase shifters, can be used using the either vector or the circuit. Wherever which are mentioned the low cost element there, this can be designed and realized, and it solve the purpose. Yeah, same thing is developed in different full antenna using those reflection type phase shifters. And since it is a S band and low cost was required, and that these bands specifically MMIC are not available to us, so we made that low cost solution with having the designing our own reflection type phase shifter and made this antenna worthwhile. Yeah, same development cycle, how these antennas architecture, various stages, performance are shown here. What are the challenges we face? How we develop it, those are things are displayed. Yeah, which I have shown that I think in the slide. The same thing which are about the spectrometer was these are the same slide, giving more detail in different way. Different scan angle, how this program will be, and it will be shown here. Yeah, now as I mentioned, the disturbing forming base is really the cutting edge having the various advantages. Here only the problem is the RF domain. If it is S band or something low frequency, we can direct digitize it. ADCs are available nowadays. ADCs are available to KU band, but they are too costly. Still, we are going for KU band direct sampling. The problems are very large in that also when you sample at such a high frequency using these high-speed ADC. Otherwise, we have to convert this RF into down converter and then apply. Once you got it down converter, then put the ADC and then put this weighting coefficient in the signal for your controller. You can achieve the very good result for you. The algorithms standards, we can apply it, and then we can achieve the simultaneous, all the elements, then we are collecting the data in the digital domain. Then the that processor, I can apply different algorithm, different weighting coefficient to generate different beams. So that kind of beams can be generated. I can create an interference, I can suppress it. All these things is very easily doable. Simultaneously, multiple beams are doable because you got the entire data. Now it's a processing and applying the correction. So these are the, there is a commercial one, IC is there, ASIC is there. Of course, this is again a key factor. If you do not have this, then you have to make all the different MMICs and that becomes bulky. This will be a useful, of course, ISRO has not developed ASIC for digital beamforming per se, but we have developed different MMIC and then did that. This is the, again, is coming into the more commercial uses for this kind of ASIC from one company is only making this satisfied, not the bigger companies. And the element block element in the previous slide there, the antenna becomes a very compact, the whole terminal becomes very compact, and like we see, and we can get a very easily scannable fast beam scanning unit. This was our digital beamforming based on the NSR recently launched 5 months back. Is a 12 to a joint collaboration between the ISRO and JPL NASA. This kind of 12-meter. This was 12-meter antenna. This is the 12-meter unfoldable antenna. This was the big structure on in space we have launched. There we have a linear array. There we have put this again digital beamforming architecture on behind that, and we are able to generate the. This is the field array of the ISRO, and this is the JPL. The field array which is delimiting the entire structure that is under testing at our phone plan. These are the beams which are generated. How it is scanning automatically, and how it is the from same single linear array and same reflector we are generating one transmit shade beam and scannable synthesized digital beamforming. These are we are used in our NISR satellites, and this is operational. Yeah, another application where was essentially required to generate multiple spot beams, multiple shade beams there, and generate interference in particular direction. There we are creating the using this DBF approach. We call it as a software-defined radio. Some people call it as a software-defined radio, or some people call it as a digital beamforming. So that it's a again fundamentally on the antenna structure level is the same. We did playing with the amplitude and phase of the excitation coefficient. These are the we did it with the reflector and feed array. There instead of if you make the completely radiating array large, it becomes very huge structure in terms of the array. So we use the reflector as a big size, and this focal plane we use the smaller array, which can generate this kind of large number of spot beams, shade beams, scalable beam, interference create from particular direction with the border size. If you want to create a null, we can create that. Anything we can do. These are the what as a ISRO we are doing this right now. It's under development for this kind of application which are shown. Some of the worldwide scenario, the best usage of this technology is done by this O3B Empower satellite. Go to the next slide. These are the photographs of O3B Empower satellite. These are the radiating arrays. If you see, they are aperiodic. They are not regularly placed, no regular arrays, completely aperiodically structured. Nearly 500, 600 elements digitally, and they are able to generate even 4,000 beams simultaneously, independently scalable. This is the NEO satellite, and that's a really fantastic example of our technology. There, in this satellite particularly is leading. Another was a Viasat E, but that having 18-meter antenna on the level. That satellite was failed by them. It was launched by the US company. It was failed. So this is still in operational. Recently launched constellation is nearly complete, not fully complete, but this development of digital beamforming or FDR-based approach phase array. This is the really the leading example of this technology. Go next. Yeah, some of the example I have shown here is our navigation satellite. This is not a steerable beam antenna. This is a fixed beam antenna having the square coax feeding network. Photograph is not here. It's completely a very complex feeding network. This is tri-band satellite, tri-band antenna. This is these are the patches having the generating circular polarization and the different bands L1, L5, L2, and S band. Three bands are there, and the generating the very good laptop beams. This is rather than because the navigation is essentially required to have effective SOTP power constant over the entire region. So that was an exact fixed beam for the network so that it could generate a very laptop beam on this at S band. See, there is a mixing of the array. S band is interviewed with the L band elements and further higher L band limit. So this was another very good example. There is another example of multi-beam array antenna for UAVs recently launched. We have launched, there are three satellites we have launched. Our navigation satellite. This is our GSAT-20 high throughput satellite communication satellite. There, so normally from single aperture, if you get this one kind of beam, we get this kind of, let's say conventionally I get narrow beam spot beam. If I have the same aperture without shaping, without how can I generate a wider beam to reduce the number of elements? So we have to generate primary pattern such a secondary pattern such a large. What we apply the concept of here is generating. Again, we played with the concept aperture theory. We put the illumination in such that field size where we can generate nulls and side lobes, eliminating this parabolic unshaped reflector. We could generate this kind of light dome. This was also a novel idea. We applied it and flown it, and that has reduced the number of hardware on board and serving very good application. Yeah, this is one of the examples we are trying for the Chandrayaan-5 or UPEX lander. Again, a very technological model. Conventionally, if I want here, I have shown here for lander, we need altimeter information correctly, altitude information correctly. Here is the location of on the lander, the altimeter, carbon altimeter antenna. Conventionally, we need this kind of four beams. These kind of four beams from the northern direction, three at 120 degree apart and one is northeast. And effectively, we need a four slotted array antenna where for this application. This size will become 400 by 360 mm entire size, carbon set. But if I want to, since it is on the, when we go interplanetary mission, the major challenge involved is to reduce the mass, reduce the power, reduce everything. So one of the technology which we are working on, we have designed and loaded for fabrication is to using the concept of peripherally excited antenna with having the reflecting lumbar lenses and the artificial dielectric layer, we could generate. If you see here the sidewise, if you change the sequentially, we are able to get this steer the beam. Effectively, those kind of four beams we are generating from the single antenna. This kind of single antenna we are able to generate. So this kind of four antenna will be replaced by the single. Size will be lesser, mass will be lesser, and will serve the purpose. That's the technology we are working on. The concept is based on these are the this structure is profiled. These are the this appears to be uniform, is not. They are small pins of nearly 10,000 pins are there in a small size of 200 mm. This kind of sharp nails type pins are required to fabricated precisely. Again, this kind of the structure, and this is the continuous transverse club. This is also very challenging for fabrication, which will generate the conceptually four beams, variable beams, and will replace this. This is we are developing. The design is over, and we develop for going for fabrication. Concept is based on the basic optics or physics that we applied for the material domain, and this is the if you see the side views how it looks like. Very small, but serves significantly for the planetary mission. So this was our for navigation Doppler radar. Okay, again, this is the concept of Broadman lens. This is not ours, this was published very old back, having some different application. I will not go into that. But we have applied much more advanced than this and for a very practical application. Okay, this is near field phase transformation. Again, as I mentioned, beam can be steered by simply rotating. This phasing is done by near field phasing. That no, we're not going. The concept is used is the transforming phase of the antenna near field between these two layers and using pair of totally passive meta surfaces and only one dimensional phase rotation we are able to rotate the beams in different directions. That's the concept here shown. We have developed one particular. We have put some photographs on one paper, but we have hardware developed one small scale. This is also a very good application, but we hope that whatever I just mentioned, the meta surface with single PCB, that is much more appealing that we are using rather than this. Yeah, this is the one more advanced of the application of near-field phase transformation, variable inclination continuous transversal concept. It's really excellent. This is also is recently published but made operational by this company. Good concept. Right now we will not go into that. Another is the domain of the lens as well as the electronic scanning, varied index lens and transformational optics. This is the field, the transformational optics is being used to apply generative. Basically, microwave is nothing but the derived from the physics of optics. The concept can be applied. You think of something, if you have a good physics and optics concept, then you can apply it to the extent of microwave antennas or microwave field. This kind of very excellent piece of this, the isotopic company has developed this for the similar application, ground-based application. I'm not going to the detail right now. Yeah, this is another area of research is essentially required. Still, a lot of work is required to be done on this domain is the directional modulation technique. Note that this is not only the aperture plane, it's now the concept of modulation you apply to steer the beam. That concept is still in the working of creating an interest in the various researchers for how we can use it. It will be very good for the terrestrial communication and a lot of application. If this goes through, then hardware cost again will come down significantly. The similar was concept. The concept what will happen instead of the conventional like this, it will become like this. This will generate a directional modulation using RF switches. Here shown the conceptually, but there are various ways of achieving this approach differently. Yeah, this is the very futuristic source phase-based because right, the requirement is the capturing the solar power, transferring to the ground. The space-based solar power system is the because in the ground also we are having a lot of solar panels, but again depends on the limitation of the land available or the area available. Nowadays people are doing on the water also solar panels and generating the power, but again it depends on the availability of sun continuously. In the rainy season, availability is very less. But in space, there it will be 24/7. The sun solar power is available. No crowding, no seasonal dependency. But the problems becomes very manifold. To capture the power is easy, continuously transferring down and making it converting into the again RF because DC power cannot be transmitted to be converted into the RF and again rectina will be used that is converting the rectified the DC or the RF into the DC and this way. So this will be these are the various technologies that we work. These are I'm showing some photographs. Still, this is not a foolproof solution has come. There are still in the infancy, but there are very innovative concept people are solve the energy problem. We had also initiated this activity and we had also developed retina, but I will say it's still a peanut. The kind of technology required is enormous, large funding in terms of this huge fund.
Sir, what is the role of antenna?
Here, there are two types of antenna. Role is very critical. If I have to capture the power, solar power on the, one is the size of the solar panel will require square kilometers of array. Now imagine the right now we are talking 15 meter or 18 meter antenna, उसी में हालत खराब हो जाती है. तो अगर उनको स्क्वायर किलोमीटर्स ऑफ एरे अगर ऊपर भेजना है, what kind of technology you will have? There itself is the question. Now, then the technology of antenna will be tethered antenna, small antenna, but it will be a swarm of antennas. They are flying in the formation plane and like acting as an array without connecting. Okay, that kind of technology is essentially required for onboard. Then, because that each antenna will have the connecting from the solar power, solar array, photovoltaic cell to the RF, DC to RF, and this will act as a transmitting, as a radiating element in huge array. Where to just imagine it may be size of more than the size of the Nagpur city, because then only it will be viable. Otherwise, there is a loss of power in transmitting from space to ground. The first question comes to viability of this concept. Whether it is viable, I am generating huge fund there, spending technology and getting transferred down. There will be because microwave power, there will be a spreading loss. So those things, the antenna technology on board is itself is challenging. What kind of such a big size array you will make it? How you will make an array? How will in phase it and then down the beam towards the display again? इसमें भी अगर pointing direction अगर आप गलती हो गई तो power इतनी use होगी किसी को जला देगी. It will become so there you need a really precision in terms of beam pointing also, and such a large few tens of kilometers of even more square size of size of the array. That's the technology in there itself. Another is retina. I will say retina, we did this kind of technology converting the RF into the DC power. To transfer RF power, we will give the DC. This is still a lot of research has done. This is mainly this kind of technology is useful for the right now we are here. Lot of RF energy is still there because all cell towers are transmitting energy. There is a technology available. They will be taking this RF signal, converting into the DC, and you can charge it. Of course, that will be microwatt and milliwatt, but still can charge the recharge or some of the device.
Wireless power.
Yeah, wireless power, but wireless power will be उसको charge करो. But still, I am gathering some power which is already in the surrounding. So the retina is still a lot of research. It is having the though the power captured is less, but here the power retina will be the huge power because you are converting. अगर viable बनाना तो I need few hundreds of megawatt power which is converting, getting back. Then only it becomes viable of spending so much money. Various concepts are floated by different space agencies. Ours is still in the infancy, I will say, because funds required is enormous, so that we have picked at slightly lower base. We have done that some. There is a decadal plan, decadal development probably because in Bharat कुछ समय हम शायद बना लेंगे. That's the time. Yeah, yeah. This is just one of the photographs I mentioned. How they are beautiful concept onboard satellites capturing. So we don't really essentially need innovative moving parts. This is the NASA concept I'm showing. I'm just giving a thought for your mind to how to have different approaches. Capturing power and getting automatically all the time so that they will be pointing towards sun. You will not to physically rotate anything and will get power. And directive antenna will be the antenna here concept. This direction से आया उसी direction में power करें without using any phase shifter or anything. So those concepts are applied, and this is the solar base. The project name is called Cassiopeia, Constant Aperture Solid State Integrated Orbital Phase Array. So as our topic was phase array advances, these are the advances of phase array. Still under the development stage, but it will see a ray of light in the on-grid orbit. So there are a lot of ways of doing it. Technological are different. Only how you apply the concept and do it, that only makes the technology, newer technology are getting emerged. Yeah, flexible I have mentioned on sheets. I will just want to go next one slide. I want to show that. Next. Thank you, goodbye. After the slide, just memory तो मुझे बता रहा था. We had also developed one membrane antenna, which is under measurement, which are like these are membrane-based antennas rather than having a solid substrate durable. This is we developed antenna for Venus orbital mission. So one of the options is right now we are not frozen on this option. There are pros and cons of this. But say there are various ways of doing this kind of antennas or in terms of using the material, using the approaches. Different technologies are getting emerged. Yeah, that's all. Thank you. If you have any questions, you can ask it, or you can reach to me by this MB_margin.
I have a question, sir.
Yeah.
So what exactly is this software defined radio? And how it is different from that hardware defined radio? And what are the applications of it? And this software is used to design software defined radio. And the last, do we need a physical antenna for the transmission of the software defined radio signal?
Yeah. Go back to, I have shown you two examples. Go back. इसको presentation से बंद कर दीजिए. Software defined radio, it's another name for the digital beamforming base approaches. Basically, why it is called software? Because by changing the software or changing the excitation coefficient, but through command line in the software, I can steer the beam, I can shape the beam, I can change the direction of whatever required. So that is the part why it is, the software is able to control entire thing. Basically, ultimately for transmitting, you ask whether hardware is required. Yes, hardware is essential. But सिर्फ मुझे हाथ पैर घुमाने के लिए दिमाग में काम कर रहा है. मैं दिमाग is the software. तो assume the दिमाग में और hardware ही को use करते हुए, but hardware physically will not be moving it. It will be only by changing the control of the excitation phases, you will be able to steer the beam, generate multiple beam, generate interference suppression, whatever you want, you can do it. Because all this power, you are sampled into your domain, into the digital domain. Okay. Then you simply by processing it, you can generate. Even you can do it in lateral processing also. You have got the already suppose काफी बड़े intelligence there are I'm not told that in the space flight application there are alien satellites are called electronic intelligence satellites. They simply move it and gather the data. Okay, gather the data. मतलब उनको transmit नहीं करना है, उनको सिर्फ intelligence gather करना है. तो intelligence gather करना है, it's an array, wide frequency band. Hardware is essential for working over this band. Once it's gathered, converted into the digital like this. Let's say this RX, whatever you have received, sampled by ADC, whatever band, either this can be converted down, as I mentioned, this can be down converted till the ADC support whatever the high speed. Once the down converted into the ADC, they are stored into the single FPGA boards will be able to do it. There, this FPGA software tool can now. जब मैं डाटा मेरा पूरा आ गया, every minutes का भी पूरा space sample कर लिया, जब इंटेलिजेंट सैटेलाइट प्रोसेसर में वो करेगा कि मेरे को अभी पर्टिकुलर डायरेक्शन, लेट्स से आई एम फ्लाइंग ओवर चाइना और पर्टिकुलर रीजन, लेट्स से बॉर्डर में मेरे को करना है, देन आई विल चेंज द एक्साइटेशन कोएफिशिएंट, व्हाटएवर डाटा आई हैव, आई विल सी व्हाट पावर पर्टिकुलर डायरेक्शन में मैक्सिमा क्रिएट करूंगा। जैसे आप नहीं करते ट्यून करते, पर्टिकुलर फ्रीक्वेंसी ट्यून हो गई तो आपको सडनली सिग्नल ज़्यादा मिलता है, वैसे ही अगर आप एक्साइटेशन ट्यून करोगे यू विल गेट पर्टिकुलर डायरेक्शन सिग्नल ज़्यादा है, उसमें से इंफॉर्मेशन निकालने की व्हाट इंफॉर्मेशन सेम डाटा से आप नया इंफॉर्मेशन एक्साइटेशन कोएफिशिएंट ट्यून करो, you will get some other regions का intelligence की information भी आ जाएगी. So entire thing is, even you can do it post processing by later date also. This is very effectively used in LED satellite, and the software is able to control the entire the steerability, reconfigurability, and all that. That is why it's called software defined radio. Radio means radio communication point of view. But effectively back of it is the digital mainframe. And this is not only in the satellite domain, but on the terrestrial domain also is the MIMO or the LTE base, their base station, they are also essentially leading this kind of software defined radio.
So how the beams will get steered, that is totally controlled by software.
That's right. Because ultimately you are doing, अगर मेरे को सपोज ये अरे था, लेट्स 9x9 का 3x3 का, मैंने सबका इंफॉर्मेशन सैंपल करके रख लिया है, अभी मैं इसको कम ज्यादा करूंगा तो मेरा एक अलग पैटर्न होगा, तो उस डायरेक्शन का आएगा तो मैं इसी इंफॉर्मेशन से मैं पता कर लूंगा कि मेरा क्या था. तो सेम चीज इज डन by having the software control. The name came from that the software defined radio, but it is basically, it's not only software, it essentially requires the hardware. And as I mentioned in the next slide, the what you mentioned, the chips are very much essential. Otherwise, the hardware becomes. And these are application specific ICs are having a lot of functionality. This functionality are getting merged into the single IC. And then each IC will be essentially required at each element. Or if suppose this is having 8 channels, at least it will cater 8 elements. But the array is big, then there will be some IC. Otherwise, use hardware is required. Hardware is must. Without hardware, software is not able to do the really communication. Whether I am answered right?
Sir, for antenna reconfigurability, there are various types. We can have the frequency reconfiguration pattern, radiation pattern, or polarization.
That's it.
So, depending on the application, how do we choose that which for which way we have to go, or do we have to go for the hybrid reconfiguration? So, how
Okay.
it is decided?
Now, the application was first will say, let's say, frequency reconfiguration. Now, frequency reconfigurability essentially, let's say, why this frequency reconfigurability is required? Because, let's say, this will be essentially required for the defense application. Okay, what happens? Suppose I'm having communication. In fact, one of the cases we have used that on satellite, but for very low frequency. I'm using a communication in, let's say, X band, let's frequency 8 gigahertz. And my Shakru knows that, the enemy knows that they are having communication. They will purposely transmit in the same frequency band some noise. Then my communication is got better. Yeah, if they are jammed, then I need a frequency reconfiguration. First, to detect that there is a detect will immediately know your SNR signal to when you will get to it. Then what you need now, communication is broken. Then I have to adopt the technique. Either one technique is create a null in that direction and still continue in the same frequency. That I showed is the interference suppression by any of the different techniques we can use it. But if that is not enough, if that is not adaptable, then I will change the frequency. By changing the frequency, if in the antenna domains, you can have either a wide bandwidth antenna or a narrow tunable antennas. Tunable antennas के लिए भी आप वेक्टर से या पिन डायोड से भी ट्यूनिंग कर सकते हैं, so that many times people tunable narrow band antenna, because if I have already antenna wide band, तो जो noise आ रहा था वो तो आ ही रहेगा, that may still have that. So I would like to prefer is a narrow band tunable antenna. So those can be done by technique like frequency tunable antennas, there are domains. Using the again vector, you can basically you have to change the resonance frequency of that. The tunable antennas can be changing the size, changing size of the patch element if I take in simple case, और changing the वो कैसे change होगा frequency? अगर उसका मैं size change करना है तो मैं different size पे बीच में lump element लेता हूँ और उसका मैं कुछ change करता हूँ inductance और capacitance तो उसकी effective length change हो जाएगी तो मेरा उसका resonant frequency will shift to either high or low. Accordingly, the frequency reconfiguration tuning and so that way there are again what I have shown is reconfigurable antenna mostly in the beam reconfigurability or the in that. But each domain, there are some ways of doing it. Like frequent polar, now if you may say the polar, sometimes we call it polarization reconfigurability. Or the another polarization reconfigurability, either you change the CP, LSCP to RSCP, those are still selectable, you can do it very easy. You have both polarization, switch the polarization RSCP to LSCP port, it will provide the diversity in that. You choose linear horizontal to linear vertical, that is possible. Or if it is really linearly tunable, there also their structures are there. You can by either mechanical rotation or by electronic circuit, you can change the polarization. Those things those technology are also available for the polarization reconfiguration. So frequency reconfigurability mostly in such kind of defense applications they are doing it. In fact, they don't want to if this some secure communication is going on, then they don't want to disclose or continue. Sometimes they use particularly purposely changing the frequency. Some information in F1, some information in F2, some in F3. That way are also using. तो मुझे किसी को पता ही नहीं चलेगा कि मैंने क्या भेजा. Security purpose are essential. Foolproof communication from anti-jamming. Anti-jamming के लिए तो एक मैंने बताया interference suppression is one way, but purposely my entire information is not going in a single frequency. That way is also for that frequency configuration.
Sir, what are the challenges to fabricate metamaterial antenna, metamaterial based antenna?
Okay, I have shown some of the example. Was it difficult to fabricate? Simple
So,
example.
to getting that metamaterial for our end for academic projects.
We have to. Yeah, I will show that question. Simple, मैं simple example बताता हूँ. उसके लिए academics के लिए भी कोई problem नहीं, कोई problem नहीं. ये जो बना है एक डिवाइड का सबस्ट्रेट आपके पास होगा या इवन FR4 तो होगा आपके पास अगर आपको वर्क करना है अगर FR4 is probably available everywhere in academics if not derived and it's what is required to design इसमें अपनी फोटो में आने रहा है जो structures the meta element design that is printed structure what I shown in the one of this the previous yes. Just ये element है. This is just printed. ये मैंने दिखाया बाकी भूल जाइए ये तो reconfiguration मेटा सरफेस के लिए मैंने इनको चेंज करके इसकी इफेक्टिव डायरेक्टली कांस्टेंट फाइबर में थोड़ा नेगेटिव ला सकता हूँ वो स्ट्रक्चर डिजाइन करना है जो कॉम्प्लीमेंट दिस इज जो एलिमेंट है कॉम्प्लीमेंट इलेक्ट्रिक रेजोनेंस यू कैन हैव सी आर सी different type of this is very much doable by academics realizable also there is no fabrication difficulty the material point of view is also no problem design problem is it is your own idea tools are available papers are available you can use so the meta material is not and something people many times have misconception it's a different material having negative band or negative E or the combination it's you have to generate artificially that element by having some kind of design, structural design. That is the, but it is very much doable by all the academicians. Any questions? Okay, thank you very much for giving me opportunity to And you can anytime contact me. I will be always, I can respond to it by mail. I will be I can, I can be reached this phone number, Anand के पास है. You can contact, give me my number. You can drop me a mail, you can drop me a message, I will be able to reach you. Even, I was discussing with madam, if some of you needs to work at ISRO for some of your PhD topic or some of the research, you need some facility, we can extend some your stay. You have to arrange for your own stay, but we can help it in. We will not pay for that, but we will provide. We will extend the facility, what the measurement facility, fabrication facility, all the design tools available at the. I can commit for the site from the Space Application Center in Ahmedabad. We can provide those facilities. 4 months, 6 months, and conduct the research, develop hardware. That we can win, provided it is a win-win. Your topic of interest is also having some connection with you or some correlation with you. We can always provide all the kind of support. You can, since all your faculty, you can send your students also for some internship. Nowadays, we are preferring at least more than 10 weeks or more, and that to prefer if it is slightly more duration, it is preferred because ये 2 महीने में बच्चों को समझने में टाइम लगता है क्या है क्या उसको करने में टाइम नहीं मिलता है बट इट इज सिग्निफिकेंटली सम 3-4 months टाइम इज अवेलेबल if you are PG student or BTech student in last semester or project semester, we can provide some opportunities for working with us, providing some internship there. So these are the way. Some of the collaborating with ISRO in general is the sponsored research respond project you might be aware of. The entire information, the problem definitions are displayed on the ISRO website under the name of Respond, that is sponsored research, and you can see different center, not necessarily Ahmedabad, all over ISRO, different center have different problem definition. You can choose whatever suitable for you, submit a proposal. Normally it is displayed in December end or January mid, around that, and then you have to submit before the deadline, some March or something. And then the proposals are evaluated, and then according proposals are invited all over India, and then allotted to the best out of them. And don't get biased that it is only for IITs or NITs. It's not that. We have different opinion for few IITs, there is separate IIT cells, but we prefer that is some 2-tier or 2nd-tier or colleges, they are more sincere toward the problem, but so we prefer to allot to those colleges rather than giving top IITs. So that is, we have over the experience we found the people, what we need is the sincere effort into that problem definition. So that is, it's not that the IIT only can do it in good research. We strongly differ from that opinion. Not me as a whole, other ISRO coming fraternity, we feel that what we need is the sincere effort in those directions. If our researchers can put sincere effort, certainly output is at par expense, it can be achieved. That doesn't require IIT power. That's these are the ways of collaborating with the ISRO for different research. Thank you.
Yeah, I'm very much thankful, sir, to you. And it was insightful session, and what happens in ISRO, we don't know. Otherwise, it is only available on net and through television. But through this direct interaction, we really have this insightful session. So I'm very much thankful to you. I request HOD ETC department, Dr. Jaya Kanage madam, to please present the memento.
Thank you, everybody. You are always able to contactable by giving email or phone. You can, without hesitation, you can reach me. Anybody can. Thank you.
Thank you.
Sorry,